Buonasera a tutti.
Good evening.
Buonasera
also to those who are late, and welcome to GiovedìScienza, the beginning of the story that we're going to talk about probably is in the 50s, because I think it's 1951-52 that the National Institute for Nuclear Physics was established, and it was a decade that was particularly lively for Italy and for science. And you also had Fernando Ferroni, who was born that year. I was going to give his name later, but at this point he is now being revealed. And CERN was also established on a European level, and not by chance, because science and physics had to overcome all the barriers, and research might be based on international cooperation. Italy maybe lagged a bit behind in the following decades, but not the National Institute and Fernando Ferroni, who remain there solid to come to this day and age. This is in Italy, but on the other side, and our second guest might tell us, but it is certainly true that in the past decades, maybe 20, 30 years, China has experienced a major economic development which has gone hand in hand, and our guest will tell us whether it's a chance or a political decision. I was saying it has gone hand in hand with the development in research. The most recent episode that I would like to mention is on January the 3rd, the lander with a rover that landed on the hidden side of the moon. We won't be talking about the moon, or maybe we will, but in any case, we will be talking about international cooperation that are necessary now, were necessary in the past, but more so. We will be talking about particles, we will be talking about identification of particles in the space, and lastly, I will introduce our guest, Fernando Ferroni, and Yifang Wang. Fernando Ferroni, as well as being born roughly at the same time of the INFN, became its chairperson since 2011. The audience of GiovedìScienza knows him because we already met him last year, the last time, in an evening introduced by Neri Marcore. This evening you get me. You will have to accept me, while Yifang Wang is the director of the Institute for High Energies of the Chinese Academy for Science. He is a physicist, and he attended his PhD, did his doctoral studies in Florence, so you will hear him speak in Italian. Maybe when you ask questions, please speak more slowly, but he will be able to answer any question. So let's now start working. But let us talk about when this cooperation between Italy and China, and when did you meet? These are two different things. I know him because he did his doctoral thesis in CERN in an experiment where we were together, and in the 90s, and 86, yes, you're right. We met in 1986. Ex post, I also sold him a car, a white Golf. He also told him that he sold it for more money than he paid for it. This shows that the Chinese are good businessmen too. But scientific cooperation, which is not the one between us, but between the Institute of High Energies in Beijing and the the INF started in the 90s when the Chinese decided to build a cosmic ray detector in Tibet, which is particularly suited for that because you can stay at 5,500 meters. There are there's no electromagnetic nor human problems up there, no signs. But we could therefore carry out an experiment, but with a detector that didn't cost too much, and we had the suitable technologies these resistive counters that had been developed in Italy at the time. So an Italian group went to cooperate with them in China. I've never been there, but they told me things that you humans would never imagine. It was very beautiful, everything worked very well, but they were all talk about how they were eating. In China, food is wonderful, but apparently in Tibet, it's not basically like that. But from there, and this is important, not the food, but this I'm about to say. Well, the food too, the food is important because you know how important it is for Italians, but it means that in spite of the fact that they weren't eating good food, the fire of physics and the importance of the relationship with our Chinese colleagues helped us overcome the problem. Hence, the great adventure which we can talk about and that has gone on and that maybe he can describe better than I can, because many of the things that we do in China with him. I don't know if we want to start with there, or since we have prepared some slides, we could start with them and with particle accelerators. If you would like to comment it, that would be better. Well, it's in Chinese, so I think that's the best thing. This is an accelerator. We are working with the INFN. It's an accelerator with 100 kilometers, the circumference, and it's electron-positron collider. So this is it. This is the plan and the design, and you can see that this is the explanation of how the machine works. This, for the time being, is a design, and it is Wang's idea. They've been talking about it, and when do you think will it be built? We have started with this idea we started in 2012, when the Higgs boson was discovered. We had a discussion to see what could be done in the future, and we had this idea that in future we would need an electron and positron accelerator to study the Higgs boson, and a factor 10 here compared to what the CERN accelerator can do. So this is the idea that we had, and we started in 2012 and have gone on. We already have a plan. At least we have the concept. Please excuse me, but in Florence they wouldn't forgive you, but here we're in Turin and they will forgive you. Some time has gone by since your doctorate, so you might miss one word or two. Here you can see the machine. We worked on it. We've been working on it for the past 6 years, and now in CERN 2, they have roughly the same idea of having a comparable machine with a circumference of 100 kilometers. This announcement was made on January the 15th this year. This also means that on a world level, physicists have the same idea for the future. That is to say, an electron and positron machine is the future for particle physics. Well, what about how long will it take? For the time being, it's only a design, and if everything works, In about 4 or 5 years, you're going to start building it? Yes, if everything goes well, we can start building this machine in about 5 years from now, and then you need nearly 8 or 10 years to complete it. So we think in 2030 we will have it operational. Tomorrow, the day after tomorrow, yes. Well, if you consider the scale of our experiments, 2030 is very soon. And Geneva? Well, in Geneva, we are developing a similar project. How much time do we need? I don't know. Certainly not for 2030, because Geneva already has an accelerator that should be working until 2036. So it might be conceivable that an accelerator of this type might be ready for, say, 2040. I think that's reasonable. Yes, they've said about 2040. I believe that 2 accelerators like this will not be built. I think one of them, but I live in a global world, and for me, it's fine. Whoever makes it, it's fine. Physics is a worldwide one. Physicists don't have any prejudice. There's no sense in having 2. For example, on the same collider, there's an enormous investment, so there might be, say, 10, 12 billion of euros. I don't know. I don't know in yuan how much it would be, but this is the order of magnitude. To have 2 experiments on the same machine would add 10% of the cost, while if you have 2 colliders, you double the cost. Why don't we then carry out 2 experiments on the same machines instead of having 2 different machines? A minimum of common sense, which is what physicists has. Not altogether, because otherwise they wouldn't be doing this type of work, but they have some common sense. So let's talk about the present. Since we were speaking about the future, well, let's now come back to the present and talk about accelerators and cooperation. There's a beautiful machine in Beijing, and it's called BESS, and it has been working since 2009. I think that it'll work for another 10 years, yes. There are Italian groups that work with them. Maybe he can tell us what they're doing, because I'm putting the money into it, but they work. Yes, we have a group of Italians who work on this machine. They have done a lot of work on data, and the results have been good. We have also a cooperation with the Juno experiment near Hong Kong. This experiment, well, Yifang, near is a Chinese definition. It took me 4 hours and a half from Hong Kong. Well, it's only 100 kilometers. Yes, it's not easy. Now there's a bridge, isn't there? Now there's a bridge, so it's much easier. So this experiment has had a big contribution from INFN, both in terms of money, but also in terms of people. So there's a big group on this experiment. In this case, are they from the Gran Sasso lab? Well, the experience for Juno comes from the Borezzino experiment, which is carried out in the Gran Sasso. But the people who went there very diverse. They come from various parts of Italy. Something that you may know, INFN has 21 Italian universities and 4 national labs. So when a person has carried out an experiment, they may have performed it in various places. Now let us say 27 kilometers to discover, 270 meters to treat. So it's also be used for medicine. We spoke about it last year. Here you can see the machine the synchrotron, which has a length of 27 kilometers. It accelerates particles with an energy of 878,000 billion electron volt. An electron volt, say if you have a battery, which is 1.5, is 1.5 volts. So if you put a few billion batteries, you will get the energy of the HLC. But it's the concept is the same. Below you see 270 meters. Protons and carbon ions are accelerated at 400 million, much smaller, so it does much less. But it's the right sort of energy to send a beam on a patient and destroy a solid tumor. Not all the cancers can be treated like this. There are cancers, in particular, the ones at the basis of the cranium and in that area, for which this treatment is better than any other solution. It's better than any other solution because this treatment and these carbon ions go to destroy the cancer where it is, virtually without reducing the damage on the way. The alternative, which is the one which is called radiotherapy with photons, which is performed in all hospitals and which is fine for many cancers that are in less critical position, is that photons spray the entire brain with radiation. So having a choice, I would prefer to have it concentrated where there is the cancer rather than have the brain sprayed with radiation. If you've got to die, it's better to have, well, that's under better, but this is a very interesting option which is offered to patients in our country, and it's one of the 2 machines in Europe and which do this. I don't know if in China you're also developing a similar machine. Yes, we have a similar machine in Beijing and Shanghai, but in this case there is no cooperation. Well, there's a cooperation in terms of technology because there are people who speak to each other. Here, the most important, because technology it comes from accelerators that we know how to build and have known how to for decades, and maybe cooperation is more important in terms of the doctors working together for them to find parameters. So it is not, we don't know how you treat a patient, a doctor do. Let us clearly identify who's doing what. Well, in this case, like the one of the INFN and CERN, the spirit is that of sharing data. You don't hide them, you don't keep them. There's no war on the copyright of discoveries because the technology that is developed to one side here, look, here we're talking about treating sick people, and I think that is the most important. On these machines, there is no particularly proprietary technology or copyright. We know how to build an accelerator. We know how to direct a beam, as long as you tell us where the beam goes. But thereafter, there's someone else who has to deal with it. In this case, too, there should be a video. So if we can show it. The video is on HLC, so here it is. We spoke about it. It is the machine which we invested on, well, the one we've spent more money on in the past 20, 30 years. It's a little jewel of technology, and this is a global machine, as we say. Everybody's taken part. Physicists of the nation-states that built CERN, the physicists of countries who subsequently joined CERN, but anyone can cooperate as long as they have an idea, they bring a contribution to one of the experiments, and they are then accepted. This machine has no boundaries and no barriers. I think this is one of the hallmarks of science and of particle physics in particular. There is no barrier at the entrance. I think that on this machine there are Iranians and Israelis, Palestinians, and anyone else. I think that the map of those who are working at CERN coincides with the United Nations, as long as there is a university interested in doing these things. Physics goes beyond the barriers, cultural, religious barriers, political barriers of any kind. We have never asked, well, we can ask you, people, do you know what Dirac's equation is, but not what is your religion. And it is a center that could inspire how you can agree beyond the disagreement that exists at another level. CERN Center, CERN, is very important because of this. Science goes beyond politics, but it needs politics in terms of choices, of policies, because for research such as this, you need a lot of money, you need a lot of people working there, not just a lot of scientists, but a series of technologies and industry that is up to it, therefore an investment, an overall investment. Yes, yes. I was hoping for some more comprehensive answer. Well, we can talk about it for a long time. I'm curious to know what it's like in China, what the relationship between industry and the people who fund it is. In China is no different from any other country. So we carry out this research in science, and to do this, you need industrial backing. So we have quite a close relationship with our industry. This is very useful also to have a political backing. So clearly this research not only is necessary for the scientific results, but also to have we need help from industry. Yes, this is very important. When we built this machine, the Italian industry also took some orders which exceeded the investment that Italy paid into CERN as its share. And this happened because INFN, through a series of prototypes, then made it possible. That is to say, taught, in inverted commas, industry how to do it. When you do this, then the government realizes this, not because if I go to explain it, it probably won't work, but if industry says that you have to continue this line of research because it develops skills and ability, and this means that it helped to develop markets that go beyond this, because, for example, the industry that developed the magnets then also got the one for ITER in France. It's a fusion reactor. And China takes part too, yes. These have become global companies, as has the competition. Competition is good because it gets you to do things better. You do it better and more quickly. So I think competition is always welcome. Talking to Yifang Wang before the conference, we were talking about the fact that China in the past 30 years has seen its economy increase incredibly, as also investments in research. I would like to know if this was an enlightened decision, while he was saying that it's by chance, more or less. Why don't we get the same chance? Well, because the economy increases by, in China, about 10% a year for the past 30 years. So the support of the government for science has maintained the same level. This means we get plus 10% a year, and it's not something special for science. It's the same as any other sector. Aren't they lucky? If it were less than that, we would have, if we had more than that, we would have had special support. If we had less than 10%, no support. But we maintain it a par. So it developed hand in hand with the economy, while we are in a country where the economy stagnates, so they're giving us even less. What about our figures? The economy in Italy, well, you can read this in the papers. But in terms of the investments, when the economy doesn't grow, there are two solutions. One is the German one, saying the economy doesn't work, but we will invest more in the knowledge economy, so to help them. Germany is not growing at an incredible, because I think as the rest of Europe, 1%, 1.5% a year. But they've given 3–4% to science. So Italy saying we cut, the economy is not good, cut money for science, and we'll put the money elsewhere. I won't give you any opinion on the end results. And we'll leave it to our future generations to say, what have we got here? On the left, the red object is the electromagnetic calorimeter, which is an experiment that was called L3, where we were working together in the end of the 80s. L3 started in 1989, but we started working on it in 1980. And this is where I met this young, brilliant man who mysteriously arrived at the University of Florence.
Allora, quel calorimetro è fatto di 11.000.
Here we have 11,000 crystals, as you can see in the center bottom in the picture. Measures electromagnetic swarms. In particular, if you look at that event with two objects that are going one way and the other one, this is one of the most important results of the experiment. It's the decay of an intermediate Z boson and in a positron and an electron. And you can see that the two beautiful things, plus a photon, which is indicated there. And you can see that that object works. But then if you take the same, this is 11,000 crystals, and it looks a bit like a barrel, like a wine barrel. And I'm sure that in Piedmont there are many of these. But roughly, there's also the size of it, of a barrique. So it's really an object which in Piedmont you should know about. So there are lots of rings in these crystals. And now take one of the rings of these crystals, just one. So it becomes a ring which you can see to the right. Now, you inject in the patient an object which is called FGT, but it's basically a molecule that contains a radioactive fluoride, which is activated in the hospital in the cyclotron, which is another form of accelerator, and that binds to yours cancer, to your cancer. No, let's not say your cancer, but somebody else's cancers, because you haven't got one. And then because it's radioactive and emits positrons, positrons immediately find the electrons and they release two photons. So on a small scale, you reproduce exactly what was produced within L3 when a Z0 decayed. Now, for the comfort of the patients, you don't show all those things. You put the patient in that machine, which you can see on the bottom left, but exactly what you have is that sort of a ring that you can see up at the top, and then the electronics that read it. And you can see in the scan of that brain, you can see, for instance, that's not cancer, it's Parkinson's. It's a brain of somebody affected by Parkinson. You can see that a normal brain, which is the one to the left, where there are the two red lobes, is different from the Parkinson one, and how it modified. So it's in means of diagnostics, which is imaging diagnostics, which is very important, and because doctors can better understand the evolution of the disease, or in the case of cancer, they understand it's a cancer. We'll see what we will do it, whether we would then operate the person with a surgical knife, give chemotherapy, or take them. We decide that. That's something which does not concern me, but that is one way to supply medicine with some tools that are from particle physics. Again, if I'm not wrong, there should be another video. Thank you. Can you go back a bit? This crystal was from L3 for the reason that the crystal is very good for research, for science. But this crystal is not, or didn't existed before this experiment L3. It was developed in China, and in the end, this crystal was built. 10,000 was all manufactured in China, and now all the PET are using that crystal in the world. So you can see how you can use the technology and how international cooperation has contributed. This is very important. That is to say, the people who manufacture it, which is a company which is in Shanghai, which is part also of the Chinese Academy, developed this crystal, which people didn't know how to make earlier on. And they also, at L3, during the experiment, these 11,000 crystals, they paid it with a price that didn't even repay the investment. But thereafter, that company has sold thousands, tons of these to hospitals for medicine, and certainly made a profit. This is a virtuous relationship. Science asks for technology, industry understands what the potential is, helps you what to manufacture it, and then makes a profit on it. That's a virtuous circle. Here you see again the video. It's a patient going into the machine. If you want to be treated, there must be something which frightens you a bit. Well, this is better than a surgical knife. Look, the patient is breathing, which means they're alive. The face looks a bit odd, but there you are. This is Knau. This is the scan that the beam of carbon ions does on the target, which is the cancer that is marked in red. because the beam can be modulated in terms of energy and space, slice by slice, eats, so to speak, the cancer. Yes, slice by slice with a program which doesn't finish in the first 5 minutes. I think the standard is 16 sessions in about a week. How a session lasts very little. Radiation in a single session, I think 2 or 3 minutes. The problem with the positioning the patient to have the beam takes about a quarter of an hour, 20 minutes. Right. We spoke about accelerators, particle physics. We have spoken about medicine. Now let us talk about art. That's what it says here. We, in Florence, but I don't think this existed when you were there, we have an accelerator that the university, when he was in Florence, it was in a beautiful place at Arcetri, near Galileo's house. From the Institute of Physics, you could see the whole of Florence, wonderful. Then they decided that it was not the best place, so we moved to Sesto Fiorentino, which is an awful place, really an awful place, and to punish us, because the Institute of Physics is in a very beautiful building, and in the basement, yes, of Sesto Fiorentino, there's this particle accelerator, which has been made especially to study pictures and sculptures and other things. But because we're in Florence, you have to pay for it, and that's where we are. They decided to go to Sesto Fiorentino because there was more space, and now there'll be an airport built very close by, and so there'll be planes coming over us or through us. We have to decide that, so unfortunately we'll have to move, but that's not the point. The point is, if you have a machine that can study pictures and books or statues, why do you do it? You do it because, for instance, of a picture you want to know 2 things. First of all, let's say that it's ruined in a particular point. I don't think it's fashionable, but you want to restore it, targeted restoration. You must know exactly what type of pigment, what type of chemical compound, otherwise it will never work. And with these machines, bombing them with protons or ions and looking at the X-rays, you can see exactly what is the chemical ingredient or element, so you know the compounds, and then also you want to know whether the painter was rich or poor, had redone things. What is there behind? Is there a test? Was there another picture that he or she thought was not good, or were they poor? So these machines can tell you exactly what is the layers. They can read the layers of the various paintings on books. So, for instance, it's very easy to date a book because the people who were using or writing the books at the time had a particular type of ink. For example, we were able to date some of Galileo's books, and you can also do the same thing on statues. But the problem is that to take a Leonardo or to take a Piero della Francesca or Galileo's books from the Uffizi to Sesto Fiorentino is rather delicate. It has been done, and although there's the airport close by, but yes, the problem is the types of traffic you have in Florence. Imagine that the director of the Uffizi has to take a Leonardo, and then I'm not talking about thieves. That's how can they know? But say that they have an accident. You've lost a Leonardo and a director. Well, that's not a problem. You can always the director is disposable, but the Leonardo is not, because you can have another director, but you can't have another Leonardo. No, Leonardo died, and so we still haven't had another one. So the point is that we thought that possibly it was better to have a machine and to put it at the workshop of the semi-precious stones known as opificio delle pietre dure. It's a machine. The only other machine is at the Louvre, and also it flooded. Do you remember that the Seine at one point broke its banks, and so I don't even know if the machine works. So we decided to build this machine with CERN for the workshop of semi-precious stones, the opificio delle pietre dure. It's a very small machine, and this is how you can read all the things that the painting will tell us. It's a very beautiful technique, and I believe that I've seen some of it, but I think that from next year it will make the workshop of semi-precious stones in Florence the best equipped in Europe. We know that museums are very poor, especially the Italian ones, because they can't sell things. In all museums of the world where I go, and I have to bring a present home because otherwise my wife would not speak to me, I go and buy something at the museum, a pen which would cost €1, but it costs €10. But the museum, it has a museum name. But in Italy we can't do this. But that said, we know that museums are very poor. So this machine will be a gift. And this is this St. Francis's shroud, is it? Yes, well, and recently we're part of a very interesting debate on history of art, which is Artemidorus's papyrus, in Italian known as the Papiro di Artemidoro, because we say, with some facts and figures, while the historians of art believe us to be wrong. We say, yours is an opinion, we've got the facts, but we're tolerant. And we're not going to have a referendum on the results. Neutrinos and whales. There would be, are there any whales in China? Are there any whales in China? No. No whales. I don't know why.
Non lo so. Non lo so, vabbè. Dunque, abbiamo un interessante esperimento.
The very interesting experiment is the one which you see here represented as if it were a ball and some threads, but it's something a bit more complicated. This experiment is anchored at 3,500 meters below sea level in Capo Passero in Sicily, in one of the fossae that the Mediterranean has. You anchor this at the bottom of the sea, and along it you can see we have some sort of electronic eyes, these that look like balls or spheres, and you must imagine the fact that at 3,500 meters below sea level there's not much light, so in total darkness you can see two things. So either one of those fish, you know, that have celacanthus, I don't know what it's called, and it has a sort of lantern and says, good morning to you, very interesting, or you can see the swarms induced by high-energy neutrinos that come from the distant skies. Why do you see them? Because neutrinos interact with water sometimes. This apparatus manages to monitor or to see a cubic kilometer of water. So every now and again you get a few neutrinos. Neutrinos hardly ever interact, but sometimes they do, so you see them. And the charged particles that are the result of this, because they're faster than light, beware, beware here. They're faster than light in water, because light in water is slower than outside. So the particle can go faster than light in water. So at that point, when a plane goes faster than sound, what does it do? It breaks the sound barrier and it goes boom. I don't know. I think that people remember it here, right? Is there a military base here? I remember it. You must be quite close to a military base where you have the jet planes leaving, breaking the sound barrier and going boom. In Novara. Maybe they bang, well, close to the airport. They have very fast acceleration. Yes, they accelerate. In any case, In practice, in water, you get the same effect, but instead of going bang, they have a light bang, so we see light. Fine, this is particle physics, your problem, as you say, and if you understand it, fine. If you don't, there's no problem. But there's an interesting problem. These photo tubes are anchored downwards, but they can't be anchored at the top, because there's nothing to anchor them to, so they float with the current so that you have at 3,000 meters. Well, I don't know. It doesn't matter whether they're known or not. I don't study the currents. I study the electric currents, but not the sea ones. When you see the light, I saw the light in this one, but where was the sphere? So you must know where the spheres are. And to know where the spheres are, there's a very simple way. Next to it, you put a sound emitter and sort of loudspeaker and a mic. So sound travels upwards, is then reflected on the surface of the sea, then it goes back down. There's a sort of triangulation which enables us to know where it was. Fine. At a certain point, this experiment started to hear noises that were rather unusual, but which seemed to belong to like clicks to beings. I was not able to transfer the audio here. Click, 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 click. And then you realize, following this sound, you realize that, for instance, you can see that movement. Those are two lines that are there. Those are two whales. The two whales that are playing together. Probably they're looking for food. I don't know what they're doing. We don't really understand what they're saying, but they're talking to each other, and this is their language. We've made progress with marine biologists, and now we know when one is male, when one is female, and when one is a young whale. But the next step would be to understand what they say. But to do this, you should have tests with monkeys. Here's the banana, here's sugar, you react. Well, to find a whale at 3,000 meters below sea level, give them something is a big problem. But if marine biologists give us a good idea, we could do it. One thing that we understood is that if you look at that whale, which is going from blue to red, which is vertically positioned, that one is actually moving in a very short time, in a negligible time. It is moving 500 meters downwards, incredible speed. This will also help us understand the ability of whales to modify themselves. In fact, these are not technically, these are not whales, but sperm whales. They belong to the same family, but they're one of the many possibilities. So the Mediterranean, at least in Sicily, is full of whales, or sperm whales. Interesting. Nice. You give a lot of information and technology to other experts. In any case, they couldn't pay us, because biology is poor in Italy, so we might as well give it. I don't know if here there's a video. We went from whales to the universe, but I don't think there are many whales up in the sky, but still, where are we? We're in our underground labs, the INFN. These are the Gran Sasso labs. They have a lab in China which is very similar to the national one of the Gran Sasso. It is currently being completed, but there is a small difference, and I must say this, that the Gran Sasso are an hour and a quarter from Rome, while the Chinese ones are in a wonderful region, which is Sichuan, but unfortunately they're 3.5 hours from the closest town, which is Xisong,
che peraltro in Cina è anche un posto famoso perché vicino c'è una delle basi
which is quite famous in China because it's very close to where the missile rocket went to the moon, but 3.5 hours in the mountains of Sichuan is slightly more challenging than going from Rome to the Gran Sasso. That said, I think that we will be doing the same things and cooperating, trying to understand what the universe is like being under a mountain. Why are you under the mountain? Everybody wants to know because we like to be uncomfortable. No, not that. No, you get there's a motorway leading there. Yes, but then inside it's not, it's always, they've always got 1,400 meters of rock above you. It's always damp. No, the thing is that to understand life, that is to say the beginning of, and the birth and death of a star, you have to be below ground. You thought that you had to look at stars. Nope. Nope. Why? Why? Well, first of all, the star has to come on. That is to say, there are nuclear reactions that have to take place. But a star doesn't do that in 3 days. Maybe you need about 1 million years for it to form because those nuclear reactions are very rare, very slow. So you must find the circumstance whereby those two things go together. We can reproduce these things. Stop that because we've gone somewhere else. This is not CERN, this is Virgo, but this is Virgo. Stop the movie! No, in any case, we know how to reproduce these reactions, but they're very, very slow. So if you want to a slow reaction, if you want to study it, you even in our labs, every 10 days you can have a reaction, but in those 10 days, outside our lab, there are so many cosmic rays that you don't understand anything. While there we have eliminated cosmic rays, which means that we can carry out measurements that are very rare. That's the birth of a star. So you eliminate cosmic rays and you created a star. No. You've studied the reactions that may give rise to a star. The best way to study a star is to measure neutrinos. The neutrinos that the reactions at the heart of the star emit. Neutrinos, as we've understood, are particles so that before they interact, you must really convince them with a piece of chocolate. They're very difficult children. They throw tantrums, so they change. They also change. That's another problem, or it's a luck or a problem. It depends who you are. And then an experiment under the Gran Sasso interact 1, 2, or 3 a day. Again, cosmic rays would make it impossible to understand them, but this is the normal way a star works. If once we would tell you through the Borexino experiments that the flow of neutrinos has changed, you should get very worried, and me too, but probably at least I know why and you don't, and I'm not going to tell you why. Thirdly, very often stars end up in a bang. That is to say, at that point, the star has eaten all its fuel, its nuclear fuel. Gravity wins. For a while, it wakes up again, then it can't, it collapses, and in that, there is an explosion, and it throws all sorts of things out, including these famous neutrinos. But the nice thing is that all the rest, well, neutrinos are specific of a phase of the explosion, which is very clear, and you can describe it. But you don't know when it's going to happen and how long it's going to last. How long does it last as a supernova? And if you don't see the neutrinos, you'll never know, because you never understand it with light. But light is something that you see ex post, afterwards, when somebody says the supernova has exploded and you see it, while the neutrinos, you can see it, how long the flow of neutrinos are, and so your model of how the supernova. Have I now convinced you that you've got to go underground to watch stars? If you want to be romantic and take someone, your partner, to see the stars, go to the Alps and you will have a romantic view of the stars, but you won't learn anything in terms of physics. You can do both things, but not in the same place. Well, we got a spoiler with that slide. Let's talk about earthquakes. Yifang, tell them what you're doing there. Yeah, with the satellite. When you have earthquakes, cosmic rays and the electromagnetic field changes, so you can see it before and after from the satellite, and if you're lucky, also during. You can see what happens to this electromagnetic field. So we can see whether in the future we can predict the earthquakes. Now we're only talking about studies. Well, it's already quite a bit, thanks to China, because this is a Chinese initiative, and we have built part of that satellite, but since we're Italians, we should be very proud that we're taking part in this, because both China and Italy are countries where earthquakes are a big problem and a high price. So it's our great interest, it's in our interest to understand earthquakes better. And as for many other things, it is important when you have a complex problem, you must study it in a global manner. You can't study one thing. You can't say earthquakes. There's a dog, for example, barking. Probably it's true. Probably dogs can perceive emissions, low-frequency emissions that has to do with earthquakes. But a barking dog on itself is not enough. But then there's also maybe a radioactive gas, radon. That might be other information. But as I was saying, you must have a network also to understand if there are any correlations before and after. For instance, if you are checking the pressure, if you are there's a place where there's water and there's pressure, and you check the pressure of that water, probably, in fact, we've measured this at the Gran Sasso for the earthquakes that we had at Amatrice. The pressure of the water changes before, because if you have a fault which is moving, that will influence the distribution of water. A satellite that tries to understand if electromagnetic radiation changes, because this changes it, all this one day is something we might put together. We don't think that tomorrow we will have results, but probably in 30 years we will know things much better. But if we don't, as some were to say, if we don't waste, in inverted commas, our money on these things, we won't manage to obtain the results. We have to sow the seed to harvest the crops. And now, first of all, I would like to ask the audience if they have any questions. And then, since we are in space, am I mistaken, or is there another cooperation? Theirs is the space. We join them, but it's theirs. As far as space is concerned, we have another project, which is that of putting a detector on the Chinese space station so that we can study cosmic rays and also to study dark matter. This is called HERD, HERD. And then we have the other projects, which we're currently studying, but we're not still only a project. It's only an idea. And what have we added to it, Ferroni? Well, we add a bit of technology, detectors, on a satellite which is currently has been flying for 3-4 years, the dumper. That is the Silica Detector. This is a Silica Detector which comes from the detectors that we are using at the HLC. It's more compact, smaller, which is on board of this Chinese satellite and therefore measures the direction of the particles that hit Earth. And we are thinking of a concept that we developed together where we can piece together the things that we have learned separately. That is to say, normally a tracer has a direction, a calorimeter, anything has a direction because it is read by an electronic instrument. So if things that come that way, you can read them. But if things come the other way, you can't see them properly. So we've developed a concept of a cube where particles can arrive in any direction, and we know how to read it in its 3D version. It's a very interesting project, and it's in R&D now, which we're doing in Italy and China. We've put about €1 million on this, on the development of this concept, then to develop it, and we hope that it will be able to go on to the Chinese space station, maybe in 10 years from now. Every now and again I say 10, 20, 30 years. I will have retired by then, but look, there's a young person in front of me, and they might think of the experiments that will be held in 40 years. There's always it's like a relay. You pick up the baton. We've done these 30 years, and then we pass the baton on to youngsters. The important thing is that concept of a transmission of knowledge and the fact that you don't feel ownership for discoveries. And as I always say, all these enterprises are in the spirit of Christopher Columbus. That is to say, if Christopher Columbus had thought more carefully with a map, because he didn't know how the Earth was distributed, but he knew certain things. He knew that it was a sphere. They already knew it. The Greeks knew it. The second one is that he knew perfectly well how long Alexander the Great had taken to go from Macedonia to India. And he wanted to go to India. So if he'd taken a piece of paper and calculated it, he would have never have gone to India. But the spirit of the explorer says, I'm going. I'm going. Otherwise, it won't work.
Tornando a quegli anni 50.
Going back to those years, the 50s, the establishment of the INFN and of its president, people say that that particular moment of development was due to the fact that people who were managing scientific institutions had more freedom than now in choosing the people who could work there and deciding who could work with them. So I'm asking both of you, considering the roles that you cover, other than the science, how complicated is it to work nowadays? Big question. How complicated is it to do things in China? Very complicated. Not easy. Because now, to do something that no one has done before is something complicated, so it's difficult. So you need time and ideas. How complicated is it to interact with the decision makers? How is it to follow all the bureaucracy that I imagine that China has, like Italy? I think that in China it's quite difficult. All projects that we spoke about, you need about 10 years. to prepare it. 10 years. Talking to the government to convince them to put money. In Italy, Ferroni? Well, there's a basic difference with China, I must say, because China too had a moment of development in the previous years where things were probably easier, because when you decide that you have to reach an objective, you can also do things. In Italy, we say like Garibaldi, meaning quick and cutting corners. In the 50s, it was all very clear. We'd lost the war. We were a country that was in bits. So whatever idea that projected the country into the future, increasing our skills, was basically accepted. And that is why at the end of the 50s they started what was called the Italian economic boom, putting all that those skills and expertise together. Italy started to improve, the economy worked well. At that time they also had lots of children. It was certainly another view of the world. I'm not suggesting now that you need a war, a disastrous war, to start the economy, start it up again. I'm not saying that, but I'm simply saying that that's what changed the paradigm of Italy. Compare Italy in the 20s to the 60s. Following that, there's a mechanism which means you have to apply for money, and there's a certain number of bureaucrats that have to decide. And the larger the number of bureaucrats, the greater the incompetence of those who have to examine the project. This is a very interesting law of nature that unfortunately is relentless and everywhere. What can I say? I can't complain. I want to say this very clearly as a disclaimer of each and every government that we've had in Italy from the 50s to today. INFN has always been treated better than any other research institute in Italy. I'm saying this because this is true. Clearly, it can't be the fact that we're nice, because I don't think that all the INFN presidents were particularly nice. They're normal people. They went, I mean, we used to go to the government. I think that INFN has used each cent that it's had from 1951 to 2019 in an accountable matter. For every cent, we can tell you what we did, what type of relationship we have with other countries of the world. If the INFN offers its cooperation to China or to the US or to Japan or to Sweden or to whoever else, everybody says, come, bring your knowledge. Sometimes beyond the money we have, sometimes our knowledge and technology is more important than the money that we have. So I think that we have defended our expertise and research skill in a wonderful manner. But the fact that in any case, in this country, since, well, let's say for the past 10 years, the budget has not been increased, which is being hypocritical, because unfortunately milk costs more than it did 10 years ago, and research doesn't only need milk, it needs new raw materials, it needs tungstens. This thing certainly isn't an advantage for us. We are doing what we do. We're trying to organize things to cope. We try to be more efficient, but at a certain point it won't work. If you want this country to become a scientific backwater and with no innovation, either you put more money on the table or one after the other. We're going to close the research centers. We might be the last of the Mohicans, but this is nothing that pleases us. Are there any questions? There's one up there.
Buonasera. La mia è una curiosità riguardo ai neutrini di cui parlava
I'm
prima.
curious concerning the neutrinos that you were talking about in the Gran Sasso lab. These neutrinos come from space. You were talking about, for instance, about a supernova, and they interact and you study them. How can you know that these are the neutrinos from the supernova and not from the sun or from the Big Bang? Is it the same thing? No. Well, the Big Bang ones, I'd very much like to see them, but we really haven't found a means of doing it. It would be very beautiful to see the neutrinos from the Big Bang. They wouldn't be from the Big Bang. They would be a second after the Big Bang. We don't know how to do it. There's an idea of how we might do it. And in fact, we've just authorized an experiment. Our Princeton friends, the crystal L3 experiment called Ptolemy, the experiment to try and see if we can do this. But neutrinos from the sun have a spectrum which is defined, a certain range. They can basically go from a few hundreds of kilo electron volts to a few million electron volts. We have 2 or 3 a day, so we can have Poisson's distribution of the probability, but the supernova ones arrive all together. That is to say, they are in 1, 2 seconds, in 5 seconds, in the actual time of collapse, you have a flow of neutrinos. And so they are never alone. They also have an energy distribution which is important, but it's not as big as it's not as important as is the information of them coming together. It's the time of collapse that you learn from the neutrinos, because that makes it possible for you to establish the way in which this object imploded on itself. There's another question there.
Salve. Perché le collaborazioni internazionali che sembra così facile
Why
sembra invece così difficile?
are international cooperation projects that seem so easy in physics are so difficult in other fields?
No, adesso va anche lui, 2 visioni diverse del mondo.
Yeah, we're going to have 2 different visions of the world. Why is it easy in physics and difficult elsewhere? My impression is that in physics there are 2 basic facts. One which has to do with maths and physics, 2 plus 2 is 4. And the second thing is that I've never seen anyone making money out of physics. There's no business behind it. There's great passion for it. You want to discover a fundamental mechanism of the universe, and there's a shared language. It's called maths. Nothing about it. Now, I know that 2 plus 2 is 4. Nowadays might be questioned, and someone might say this is your opinion, but apart from this, I wouldn't say anything else. Do you agree 2 plus 2, or what? I have nothing else to add. I agree. I subscribe it. Very clear and very brief, to the point. I explained this once. I was once invited to dinner at an association. I can't even remember what it was, but a very prestigious, with a lot of rich people in a hotel in Geneva. And so they were saying, why do you never quarrel in physics? Well, here you understand it. Because no money. So no money, no quarrel. If he and I, we don't do the same experiment, we're still friends. So why don't we just work together? As you were saying, to be physicists, you have to be a bit mad. Well, yes, you have to have a vision. Now, you can interpret having a vision as being mad or not. Well, I just quoted you. Well, you have to have visions. Now, the question to both of you is it a good moment from that point of view in physics? For physics? Is it a good moment? Is it? Yes, I think it's a lovely, good, it's a great moment because now we have finished the standard model for particle physics, and we have a problem, and we don't know how to solve it. And this is the difficulty, but It's a difficulty, but it's also an opportunity. So if there's a discovery to come, it'll be a big one. Do you agree? Yes, I agree. We have explained 5% of the universe in detail, so we only have 95%. So we get our salary, not a big salary, but we'll get our salary for a lot of time. And with this, we will close today's meeting, and we say goodbye and thank you very much to Fernando Ferroni and Yifang Wang. We would like to thank them for being here, and our next appointment for GiovedìScienza is on Thursday with Christophe Dalphard. We will be talking about relativity. Thank you very much and see you.